Welcome to Cars and Aircraft Explained. The SF90 integrates high-performance electric motors directly into Ferrari's production car architecture. Before the SF90, the LaFerrari served as the proof of concept, successfully integrating electrical power into a high-performance chassis. The LaFerrari relied on a kinetic energy recovery system, a single electric motor positioned at the rear of the vehicle. The primary function of this motor was delivering brief, intense bursts of straight-line acceleration to assist the gas engine. Relying strictly on rear-wheel assist encounters a strict physical barrier. You can only channel so much rotational force through two rear tires before the rubber breaks traction and spins. For future performance leaps, the rear-wheel architecture had reached its mechanical limit. The SF90 was designed to generate and deploy a combined output of 1,000 horsepower. Pushing that level of power entirely through a rear-wheel drive platform exceeds the grip threshold of modern street tires. The sheer force would overpower the friction surface. To solve this physics problem, Ferrari abandoned the single-motor assist model. They engineered an active tri-motor architecture completely decoupled from traditional mechanical driveshafts. By distributing the workload across multiple electric motors, the SF90 rethinks exactly how a vehicle physically transmits energy to the road. This diagram breaks down the architecture, beginning with the baseline, a 4.0-liter twin-turbo V8 mounted centrally in the chassis. Tucked tightly between the V8 and rear transmission, the first of three electric motors locks into position to directly drive the rear wheels. High-output turbocharged engines experience a brief delay in power delivery. Exhaust gases require a fraction of a second to spin the turbines and build peak pressure, a mechanical delay known as turbo lag. This chart visualizes how the rear electric motor compensates for that delay. The sweeping curve tracks the delayed spool-up of the turbochargers. The vertical spike beneath it is the electric motor delivering instant rotational force, executing torque fill to eliminate the power gap entirely. Because this rear motor handles direct rotational energy, it also allows the SF90 to drive completely under electric power for short distances without waking the V8. While bridging the turbo lag perfects straight-line power delivery, it still channels all energy to the rear tires. This leaves the core problem of rear-wheel traction limits unsolved. Shifting our view to the front axle in this diagram, two entirely independent electric motors attach directly onto the left and right wheel hubs. As energy pushes outward from these motors, they establish Ferrari's first-ever electrified all-wheel drive system. Notice the structural gap in the center. There is no physical drive shaft connecting the central V8 engine to these front wheels. The mechanical link is now entirely severed. Splitting this 1,000 horsepower workload across four separate contact patches dramatically reduces the burden on the rear tires, preventing traction loss under heavy acceleration. By eliminating the central drive shaft, the front wheels transition from passive steering components into independent, high-precision power instruments. Because the front motors operate independently, the vehicle executes torque vectoring, the active calculation and distribution of different power levels to individual wheels during a turn. This schematic illustrates mid-corner physics. The system applies positive thrust to the outside front wheel, the green arrow, while applying negative braking power to the inside wheel, marked red. This yanks the nose toward the apex, tracing a geometrically tighter trajectory than standard mechanical systems. Traditional mechanical differentials react to slip after it happens. These electric motors calculate and apply forces instantaneously, preventing slip from occurring in the first place. Electric power at the front axle functions directly as a highly precise tool for high-speed stability and steering control. Generating that level of mechanical grip requires an equal amount of aerodynamic downforce to keep the car planted against the road at speed. Airflow channels integrated deeply into the underbody and an active rear spoiler constantly adjust their angles to increase vertical pressure on the tires. An electronic drag reduction system balances this extreme downforce during heavy cornering with a flatter aerodynamic profile to maximize straight-line speed. This network diagram maps the central nervous system required to manage the hardware. The V8 engine, the three motors, and the aerodynamic surfaces constantly feed telemetry back to a central digital processing unit. Running thousands of real-time calculations per second, the processing unit syncs every moving part, keeping 1,000 horsepower entirely under the driver's command. Inside the cabin, the driver commands this massive computational network through a fully digital interface. Using the physical dials mounted on the steering wheel, the operator selects between driving modes that dictate exactly how the hybrid systems harvest and deploy their energy. When those systems synchronize for maximum output, the result is the launch sequence. The electric motors instantly bite into the tarmac with zero wheel spin. The car hits 100 kilometers per hour in 2.5 seconds, pulling entirely through its grip limits toward a top speed exceeding 340 kilometers per hour. Executing a 2.5-second launch in a purely rear-wheel drive internal combustion car is physically improbable. These metrics exist strictly because of the tri-motor architecture. In Maranello, Ferrari adopted this tri-motor layout as a standard production platform, moving beyond the limited-run prototypes of the past. The SF90 utilizes advanced hybrid mechanics strictly as tools to maximize dynamic capability and lateral grip. This configuration allows for a level of throttle response and cornering precision that internal combustion alone cannot match. In the modern era of the hypercar, the highest performance metrics require the millisecond level control of an electrified front axle.